All right, let's review what we last discussed about free energy and stability. Remember that there's an inverse relationship between the stability of a system and the amount of energy it has. So the more stability you have, the less energy. The more energy you have, the less stability you have. Any system that has a lot of free energy is highly unstable, right? So we're here on this side of the teeter-totter. System that has a lot of free energy but is less stable has a great work capacity, but it can't stay here, right? Every system wants to reach that state of equilibrium or a maximum state of stability. And so spontaneously, the system is going to change to reach that state of equilibrium where it has less free energy, it's much more stable, but also has less work capacity. During this change, this is a spontaneous change where the system is trying to reach that greater state of stability. The free energy of the system is going to decrease. The system is going to become more and more stable. And as it becomes more stable, it releases that free energy. That free energy can be harnessed to do work. There are 3 examples on this slide of this process. So let's go through them. So we've got here gravitational motion, right? So the diver at the top of the platform here, he is highly unstable, right? Just based on his location, he could easily fall. But he has a lot of potential energy associated with his position. And so as he goes towards a state of higher stability, he jumps off the platform, falls into the water, and here at the bottom, he is now much more stable. He has less free energy, but also in this state, he can do less work. He has less energy to release to drive work. In the middle example here, we have diffusion. Right? We recently talked about diffusion. So in the high energy state, the system here has all the molecules packed really closely together. They don't want to be so close together. They want to spread out. So in this state right here, you have a lot of free energy, a very unstable system. You have great work capacity. The molecules, based on the definition of diffusion, are going to want to spread out into the available space, right, until the system has less free energy, is much more stable when the molecules are spread out, and has less work capacity. Remember that diffusion, it can do work, right? Think of co-transport. It can do work as it's moving through this spontaneous change of having the molecules spread out into the available space. All right, and then lastly, we've got a chemical reaction. This is actually cellular respiration. So this molecule right here is glucose, a high energy molecule that's very, let's say, unstable, and has great work capacity. So as the cell goes through degrading this glucose molecule down to individual molecules of water and carbon dioxide, that energy gets released, can be used to drive work. And once you get now here to this state of maximum stability or your equilibrium, there's less energy here, more stability, and less work capacity. All right, so now we're going to take what we've learned and apply it to individual chemical reactions. We're going to talk about certain kinds of chemical reactions and how they either release energy or they use energy. So the first kind of chemical reaction we're going to look at is called an exergonic reaction. An exergonic reaction is going to proceed with a net release of free energy. It is spontaneous. It is energetically favorable. All right, so what we're going to do is I'm actually going to take this particular graph and we're going to sort of pick it apart. We're going to redraw it on our own to better understand it. All right, so this is, we're looking at an exergonic reaction. So let me put that up here. Exergonic reaction. All right, so we have a graph. On the, nope, I guess not. Let's try one more time. All right. On the y-axis, here's where we're going to have free energy. So free energy of the system. And on the x-axis, we're going to have time. Or you can also say progress of reaction. Progress of reaction. All right, in this direction. So if we're looking at an exergonic reaction, we are going to start out with reactants here that have a lot of free energy, right? A lot of this potential or chemical energy. So these are our reactants. And we're going to show progress of reactions. So we're going to draw an arrow, and we're going to take these reactants and we're going to convert them to products. And you'll notice that the products have less free energy than the reactants that we started out with. If you recall, right, when we were talking about the laws of thermodynamics, first law of thermodynamics states that you cannot create, you cannot destroy energy, right? You can just move it around. So if the reactants that we're starting out with have this much free energy, and the products that we're ending up with have only this much free energy, that means that we lost some free energy, right? And that free energy gets released during the reaction. Oh, try that again. Energy. And that energy gets released. Now, this difference in energy, where we started and where we end up, right? That is actually our delta G. This is our change in free energy. Now, another way to think of delta G, change in free energy, you take the G, or the energy of your products, and you subtract from it the G of your reactants. So I'm just going to use arbitrary units, okay? Let's say the reactants had 4, drew with my finger. Let's say the reactants had 4 units of energy, and the products ended up with only 1 unit of energy. Let's do the math. So G of our products, right here, our products have 1 unit of energy. From that, we're going to subtract the G of the reactants, which was 4 units. All right, so our delta G in that case, if we do the math, 1 minus 4 is going to be a negative 3. So our delta G here is negative 3. And recall earlier we talked about how those reactions or processes that have a negative delta G are spontaneous. Well, exergonic reactions are going to be spontaneous. They release free energy, and some of that energy that gets released contributes to the entropy of the universe, one of those criteria that we mentioned for spontaneous reactions. All right, so what we drew here, or what we drew on the previous screen, is shown here in this particular graph. So you can see our reactants, products, energy released, and then that comparison, right? That change in free energy here is going to be less than 0. It's negative. This is an exergonic reaction. All right, endergonic reactions are going to be the direct opposite of that. So for an endergonic reaction, you're going to be starting out with reactants that have a low amount of free energy, and you want to build them into products that have high energy. You can't create, you can't destroy energy, you can just shuffle it around, right? So in order for an endergonic reaction to take place, you have to supply the energy, or cells have to supply the energy to take these reactants and convert them into high energy products. So if you were to calculate the delta G here, right, let's say the reactants here had 1 unit of energy, and the products had 4 units of energy. That'd be 4 minus 1, which is a positive 3. That's a positive delta G, indicating that in this case, this is not a spontaneous reaction. And in fact, the cell will need to contribute energy to make sure that this reaction happens. Or an endergonic reaction needs to absorb that free energy from its surroundings in order for that chemical reaction to take place. Okay, so we're going to take what we've learned so far and we're going to apply it to a system. This is an abiotic system, but hopefully it'll get us thinking about how these metabolic reactions function in a living system. So what we have here, this is going to be a closed system. So we talked about closed systems earlier. In a closed system, you can exchange energy with the surroundings, but you cannot exchange matter, right? So matter's not going to go anywhere. So in this closed system, we're going to start on the left-hand side here. We're essentially looking at a hydroelectric turbine. So we've got a barrel that's full of water, and it's connected to a second barrel using a little turbine here. The second barrel was originally empty, and it was set a little bit lower than the first barrel. Well, naturally, because of gravity, right, water wants to reach the lowest point available to it, and so water is going to start to flow from barrel number 1 to empty barrel number 2. As the water flows, it's going to spin that little turbine. That's going to do work, and the work that it does is lighting this light bulb. This is a spontaneous reaction. This is an exergonic reaction. It releases energy that can be used to do work. Again, in this case, that work is lighting the light bulb. So at this point right here, what we see is that the delta G is less than 0. It's going to be negative, again indicating an exergonic or spontaneous process. Now, the reason why the water flows is because it wants to reach a maximum state of stability, right? So it's going to release all of its energy. That energy can be used to do work until it reaches that maximum state of stability after it's released all the energy. And so on the right-hand side, we have that equilibrium. Once the water level reaches an equal level on both sides of the hydroelectric turbine here, it's not going to flow anymore, right? If it doesn't flow, then this turbine doesn't spin. There's no energy reserved to light the light bulb, and no work can be done. In this case, your change in free energy is 0, right? Nothing's moving anymore now that the system has reached that equilibrium. Now, the trouble here, though, is this example is not exactly applicable to living organisms, right? Because remember, we are not closed systems. We have the ability to exchange energy and matter with our surroundings. So we are considered open systems. So how do we make this example here a little bit more like a living organism or more like an open system? Well, what we need to do is we need to open the system so we can exchange matter with the surroundings. So we're going to add an opening in the first barrel to allow water to constantly flow in. And we're going to open up a hole at the bottom of the second barrel to constantly let water flow out. At this point, so long as nutrients are flowing in and waste is flowing out, the system will never reach equilibrium. It always tries, right? But it'll never get there. So that means that the delta G will always be negative. There will always be energy available to do, either in this case, electrical work, or like in your cells, there will always be energy available to do cellular work. So one of the defining features of life is that metabolism is never at equilibrium. It tries to get there, does everything in its power to try to get there, but because you're always taking nutrients in and water is always going out, it will never reach that equilibrium. So this is a little bit closer to what a living system might look like. To take it one step further, to make it even more like a living system or a metabolic process, remember that these metabolic processes are not just individual chemical reactions, but multiple chemical reactions linked together. So down here, what we've done is we've taken multiple hydroelectric turbines and put them all in series. And this is akin to what you would have for a catabolic pathway, in that each chemical reaction releases a little bit of energy, and the energy is used to do a little bit of work until you reach the end of the pathway, right? So long as water is coming in, it's constantly flowing to its lowest point. And each time that it sort of changes hands and it gives up some of that energy is used to do work here to light the light bulbs.